So for my fifth piece of evidence in my portfolio, I've decided to include this Desmos. I have created all the mathematical functions in this Desmos, and the Desmos simply represents the mathematical functions, all the functions, in a visual form so that it is viewable and more easy to understand. So what this demonstrates, and the reason why I included it in my portfolio, is it shows my ability to use mathematics, abstract mathematics, to create real world results and apply it in real world scenarios, and especially in optic scenarios. And this is very important in optical engineering, as you are expected to use mathematics to replicate real world results and to predict, make theories and assumptions that all fit within the real world and are not purely just mathematical. And this is an example of one that I created. So I'll just explain. So right here is so it's supposed to represent a lens. So if I were to highlight it or use a marker, this right here would be your lens. All of this. And of course, the material that you decide to make your lens out of is your choice. You can actually also edit this in the Desmos. It lets you change the index of refraction for your different materials. Now this blue line right here represents a light beam. It's a light beam that is perpendicular to the top of the lens. The green the green line, however, it represents the light beam leaving the lens, and it shows exactly how it shows how a light beam would travel in different lenses. So you can change the type of lens you want, and using this Desmos, it will also show you how the light beam and lasers that are parallel to one another also change. So right here, if you want to change your light beam, so let's say you don't want to include a perpendicular light beam from x 9.24, but instead you want it to be a little bit closer to the lens, and then you can do that, and it shows exactly how that light beam would be traced out, how the path of the light beam. And you can change this, and why this is so important is because, well, it looks simplistic. The reason why the math is so difficult is because this is actually a real world result. And if I were to zoom out and let m change let m fluctuate from different values, it looks like there is a focal point. However, the thing is that in real life there is no focal point. With any different lenses, there is not an infinitesimal focal point, but instead a focal point of most energy. And if I were to zoom in, you can see that's exactly what's happening. You can see that the y-intercept for this line keeps rapidly changing, and what that means is that there is no one focal point for more than two m values, I mean. And this is very important because this shows exactly where the light beam, this actually shows the real world representation. So in real life, if you shine a laser through a lens, you don't create a cone, but instead something that is more similar to a Gaussian beam, which is this beam, similar to this beam right here. So you have one area with most energy, which we consider a focal point, but it's not an infinitesimally small area. And this is the exact same here. So I have just replicated this with different, I've simply used the same function, but I replicated it with different m values, and it shows. And if you zoom in, you can see that the light beam isn't actually concentrated. If I were to use more, like for example, infinite different m values, and have infinite lines instead of a limited amount, you'll better see that it's a curve. But you can see that it is a curve, and that there is no one focal point, one infinitesimal focal point where all the light is concentrated. Now I will explain how to use this graph and how the functions can be changed. So the way you can change your function is, first of all, I guess you would like to see your lens, so you can use different functions. You can apply your function here. So let's say I want to have a different function for a lens. I want e to the x squared. Okay. And let's say I want negative. There you go. So this is my new lens, and I want to see how light beams bend and the path of light beams when I shine parallel light beams through this new lens that I've created. So what I do is I copy this function right here and apply it for f1, paste it for f1, but I have to change my value for x to m because it does the calculations for calculations in terms of m. Same with f2, except for instead of m, I change it to q. f1 is the most important one because it actually shows the new path of the light beam, but f2 shows exactly where it's focused. So if I were to now do this and let me just turn something on. Hold on. Actually, it's fine. It's not very important, I guess. Okay, so as you can see, now it shows exactly how the light beams would behave through this new lens, and I can make new calculations, assumptions, and theories based on this new. I can make new calculations based on this new this new function or a new path. So you can also further customize it. Here you have your index of refraction. N1 is your index of refraction for your light beam, not light beam, sorry, your index of refraction for your lens. And N2 is your index of refraction for your surrounding material. And I have decided that I want this lens to be in a vacuum, so the index of refraction for the surrounding material, there will be no material, and therefore it would have an index of refraction of 1. However, I decided I want the lens to be created out of glass, which roughly has an index of refraction of 1.517. But you can of course change the index of refraction, and that would change exactly how how the light beam is calculated. Now you can see that at some point the light beam does disappear, and that's not because there's a glitch, but it's because it means that the light beam is being bounced back. The index of refraction and the curve, the tangent line, the angle means that the light beam is bounced back into a new path, and it doesn't calculate that new path, it simply calculates it when it actually travels through the lens. For the calculations, this Desmos, my function actually is based off of Snell's law. So here is where it shows my ability to use my prior knowledge of mathematics and physics and actually apply that to create a new result. So it's based off of Snell's law, and like I said, and that's about it. It's Snell's law and other different mathematics, which is a little bit boring. Mainly, it's very reliant on derivatives and trig functions. Mainly derivatives, though. The trig functions are not as important. There's just simply ratios, right? And yeah, so these right here is the slopes to calculate the path of to calculate the slope of the new line, and you insert the value for your slope into this function here to calculate the actual path of the line. And that is about it. So thank you for watching.